Hi everyone, today's calculus lesson is going to focus on a little theorem that we're studying called the intermediate value theorem. Now this theorem is really simple. I'm going to read it to you here in its more complex form, and then I'll put it in Callahan terms for you. So let's just read together. It says a function y equals f of x that is continuous. This is going to become important in a minute. That is continuous on a closed interval from A to B. Now this is a little slightly new notation. When you have the brackets and you're going from A to B, you would have formerly written this like this. Maybe in Algebra 2, pre-calculus. It's just the x values between A and B inclusive. And likewise, if you wanted it non-inclusive like this, just x between A and B, that would be parentheses A to B. So I don't want you to mistake this as an ordered pair. This is just saying from x equals A to x equals B. So we are continuous from x equals A to x equals B, and we take on every value between f of A and f of B. In other words, if W is between f of A and f of B, then there exists some C such that f of C equals W for some C in the closed interval A to B. And then we have this graph. So here's the Callahan definition. Here you have your A and here you have your B. So from A to B is what we're sectioning off here. Now A has some y value, f of A, which is marked here, and B has some value, f of B. Well, here's the deal, guys. If you are continuous, so no hiccups in the graph whatsoever, no vertical asymptotes, no holes, no removable discontinuities, no jump discontinuities, no oscillation, nothing crazy, just smooth sailing. That will mean, by the intermediate value theorem, that you can come anywhere between A and B. We're just going to generalize it and call it C. And that f of C will lie between f of A and f of B. In other words, we take on every y value between here and here if we're continuous. Okay, makes sense. So here's a real world example. I'm just going to read it. You can read along with me. Suppose you climb a mountain starting at an elevation of 2,000 meters and ending at an elevation of 5,000 meters. No matter how many ups and downs you take as you climb, at some time, your altitude must be 3,765.6 meters, or any other number between 2,000 and 5,000. So this is just some random number between 2,000 and 5,000. Well, you're going to hit every single number between the two. If this was your low and this was your high, then your intermediate value theorem guarantees you're going to hit every value or altitude in between. Same thing if you're driving. Like if you say to somebody, hey, I maxed out at 65 miles an hour in my car over the weekend on the highway. Well, that means that you had to have hit every mile per hour on your speedometer between 0 and 65 on that trip. Okay, moving on here. It says, why is continuity of f of x so important to this theorem? Well, this picture right here is basically a counterexample of the intermediate value theorem, because as you can see, we have a jump discontinuity at x equals 0. So what we say down here is the graph above shows a jump discontinuity at x equals 0. If we focused on the closed interval from x equals -4 to 4, we can see that f of x does not take on all values between f of -4 and f of 4. In fact, we have no y values at all between -1 and 1. So if you were looking at -4 to 4, you see that here your ordered pair is -4, -1, and over here 4, 1. So if we were following the intermediate value theorem, then we would be guaranteed to hit all the y values between -1 and +1. But because this function is not continuous on this closed interval, we cannot assume that. We have a lot of missing y values here. So the only way you can use the intermediate value theorem is if you can prove continuity of your function on the interval. Okay, so how do we use it? I have an example here for you. How can the intermediate value theorem be useful? The example I'm going to show has to do with finding x-intercepts. So this is going to give you a new tool to find an x-intercept. It's pretty cool. So example 1 says, use the intermediate value theorem to show that f of x equals x to the third plus x squared minus x minus 2 has a 0, otherwise known as an x-intercept, on the closed interval from 1 to 2. So here's your solution. First, I'm going to prove continuity. So I wrote here, since f of x is a polynomial, or more specifically, cubic function, it is continuous for all real numbers, but specifically on the closed interval that they marked for us between 1 and 2. Now this is where it gets interesting. If I find f of 1, okay, and in this space here you can actually write this. So if you find f of 1, the y value when x is 1, come up to your function and plug it in. You're going to have 1 to the third plus 1 squared minus 1 minus 2. And if you do that math, you end up getting just what I wrote here, negative 1. So you've got a point on this cubic graph at 1, negative 1. Bingo. And now let's go to f of 2. So if you do f of 2, you're going to get 2 to the third plus 2 squared minus 2 minus 2. And if you do that math, you're going to get what I marked here, 8. So 2, 8. Okay, so very small interval. We're just closing off between x equals 1 and x equals 2. And by doing the endpoints of the interval and plugging those values into the function, we see that we're under the x-axis at x equals 1, and we're above the x-axis at x equals 2. So the intermediate value theorem guarantees that somewhere between 1 and 2, I cross the x-axis if I go from negative to positive, because my function assumes every y value between negative 1 and 8, we've got to hit the x-axis somewhere in between 1 and 2. So now we're going to find that x-intercept. So look at what we do. It says we now divide the interval, 1 to 2, into 10 equal subintervals, each of length, change in x, delta x equals 0.1. We look for a change in sign to see approximately where the graph is crossing the x-axis. So check it out. You're going to take your TI, and you're going to turn it on, go to y equals, and we're going to type the cubic in, x to the third plus x squared minus x minus 2. And we're going to go to table set, second window. So second window, and I'm going to start my table at 1, and my change in table is tenths. So I'm going to go change by 0.1 or tenths, and then I'm going to hit second table, second graph. And we are going to copy down all of these y values into this table. So for 1, we have negative 1, but we already knew that from up above. For 1.1, we're still negative, negative 0.559. For 1.2, we're still negative, negative 0.032. For 1.3, I'm positive 0.587. For 1.4, I'm 1.304. 1.5, 2.125. 1.6, I'm 3.056. 1.7, I'm 4.103. 1.8, 5.272. 1.9, 6.569. And then 2, of course, we're 8. So these are all the y values that we hit between 1 and 2 if we increment into 10 equal subintervals. So we're not getting all the y values, just some of them at every 10th. Okay, so let's look at this question. So it seems then that the x-intercept lies between x equals blank and x equals blank. Well, check it out. You're probably already seeing this, but look, at 1.2, you're still negative. At 1.3, you switch to positive. So the x-intercept, or when y is 0, we're looking for when y is 0, looking for the x value, it's got to occur between 1.2 and 1.3. We are zoning in on this. And let me tell you, this is a great way to find an x-intercept, because your old techniques, factoring is not going to work. Factoring by grouping is not going to work. So this is a great way to figure it out. Okay, next page. Now repeat the process again between these values of x. So between these values of x. So watch what we're going to do. We're going to reset our table. So if you go to second table set, but now start at 1.2 and increment by hundredths, 0.01, when you go to your table, you see 1.2, 1.21, etc., and you're going to fill this in all the way up to 1.3. Now, I already have this done, so I'm just going to, if you want to hit pause right now and fill it in for yourself, you may do that. But here is what I got without having to redo all the work. This is what you're going to get. I've got them filled in here. And then it prompts me again, it seems that the x-intercept lies between blank and blank. Well, I highlighted over it here for you. At 1.2, the y value is negative 0.032. And at 1.21, it's 0.02566. So we change from negative to positive between those two x values. I filled them in here. And then I wrote myself a note. We know the x-intercept lies somewhere in between these values. Everything else is positive, so we're above the x-axis at that point. So my y equals 0 has to be somewhere here. Okay, so we're going to do this one more time. The very last table asks you to repeat the process again, 10 intervals, subintervals between 1.2 and 1.21. So you see that there. So you're just going to change your table set. You're going to keep it set at 1.2 to start. But now you're going to go by thousandths, and you're going to fill these down. Again, if you want to pause the video here, I'm going to just display these answers. Here they are. And you're negative, 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 and boom, you change to positive right here. So between 1.205 and 1.206, you have a change in the sign of your y value. So I said the x-intercept is approximately 1.205, but you could also put 1.206 here. So that's a kind of cool way to use the intermediate value theorem to kind of hone in on an x-intercept, because we know we take on every y value between the endpoints because we're continuous. Now, I also made a note here. Another way you could, this is an old way of doing things. I mean, in the old days here, you used to just graph your function. And there it is. And you can see that x-intercept right here between 1 and 2. If you do a second trace, 0, come to the left of your x-intercept, a little underneath the x-axis here, and drag a little over, and then put your guess right on top, you're going to see here 1.2055694, which is very close to what we got by doing the intermediate value theorem. So food for thought gives you another, it's a little theorem that has to do with continuity that can help you do some cool mathematical things. Thanks for watching.